Hello, everybody. Okay, hopefully you can see it on the screen share. And then one thing I like to try to do today that I didn't do last time is that I will like actually set up the extra camera here for you to see how I'm writing this in real time as well. I hope that could be fun for you to be able to see both. All right. Uh, and because of the nature of the way that I'm presenting, and I would like to encourage you to download the slides. I usually share my blank slides for students to download, and then you could follow along as I presenting the materials. So you can go to this link by-hand.ai/rag, and you'll be able to find a download link to get a blank slides. You could load it onto your tablet to follow along, or you can keep it and you have a printer next to you. You can print them and follow them. Anyway, this is the roadmap for today. I would like to share with you this mathematical equation I come up with to describe what I think a rag is. And then afterward, I talk about some prompt that implemented this equation and the way that we can index data that in order to search and provide context for the retrieval part of rag, and then indexing that involve the process, a pipeline of loading data, splitting data into chunks, embedding each chunk into vectors, and storing those vectors into a database. And then with that, how can we then retrieve those information from the database? And so if you have time, they will go through some advanced RAG techniques, even though it's beginner's guide, but we're going to use the kind of very intuitive overview of some of the advanced technique, and then question answering. So that is our roadmap. First, we start with math, but not really a scary math. It's a very simple equation I come up with that RAG, in my opinion, is query plus prompt plus context and plus large language model. And what does it mean? So first, we'll start with a query, just with a query. And normally we'll send this query to large language model. We like to get some result for the users. And then I would do something like, oh, well, I will add query into this template. Instead of sending it, I would like to have a template adding something more to the query. So first is query, and now then add some prompt around it. I'm gonna cover prompt a little bit, but then I would like to be able to add some context, add context to the query. So context could come from the database. For instance, I can take this question: how much does Tom make? And go to the database, and we use this information, we retrieve a database, a bunch of data here. So actually only 3 rows, but could potentially be more. And then because of the query, this row seem to be most relevant to our query. And then the database will retrieve this and add it into our prompt template. So we have Tom 50 and Prof added to this template. And question will be, if I just write it, will be how much does Tom make? They'll be inserted into the template. And then lastly, we'll add some kind of prompt engineering around it. So this is a prompt. I actually like to walk you through this prompt. I added some blank for us to fill out so you can see how this prompt works. So in this prompt, I would like to say, tell the large language model you are something, or respectful something, assistant. So some adjective. What would be the good adjective to add? First, or maybe I want to be helpful. So I want, please be helpful, be respectful, and what else do we want? Can you be honest? So these are the example what you want the language model to behave, and also your answer should not include something that maybe on the negative side. What you should be helpful, but you also should not say something harmful. You should not say something unethical, for instance, unethical, and you shouldn't be saying something racist, sexist, toxic, dangerous, and so on, blah blah blah. And then your responses are socially unbiased. Yeah, I don't want you to be biased. So you want to do unbiased. So this is the prompt we added to the original query. The query just how originally was just how much does Tom make? And with this rag, we augment this query with prompt, we augment this query with context, and then we send it to large language model. Eventually, we send this to the whole thing, not just a query now. We have augmented with a context coming from the database. We augmented with a prompt that specify how you like to large language model to behave. And then we feed all this information to the large language model, and now it has a lot of information. Maybe they will be saying something like, well, the answer to how much does tongue make is 50. Well, actually not much. So a little bit something like that. And then it's kind of humorous in this case. Well, not much. Well, compared to CEO and CTO. Anyway, as a professor, not making that much. So a large language model has all this information to answer the question. So that's what I think the RAG could be conceptualized in very simple equation. RAG query equals query plus prompt plus context crop LLM. And for the rest of this presentation, I'd like to just break down, take some deep dive to take you further into some of these components. And so what if we remove something from equation? If we don't have this prompt, we just like have adding context, what's going to happen is that, well, if we still take this query to populate this template with our question, and then we could still do retrieval to get the context we want using this query to retrieve the context, the data we want, and put it into the context, but we didn't really add any extra prompt. And the result could be something like you feed to the LLM, but LLM might not behave the way it wants. Maybe what if who could be something like, oh, what you could say something like, oh, you are poor, ha ha ha. So that we get the LLM that's not that nice, right? Not that helpful. So it's just a very simple conceptual example to show you how important it is to add some extra prompt around it to get the LN to behave in the way you want. Okay? Hopefully that. And what if we take even more stuff out? They just don't have context, just query L. Actually, going back to this is just original LLM without RAG. So we just query. So if you just add this query to LLM, just add the query to LLM directly, what would LLM say in this case? So one way they could say something like $25 million. That actually made me happy. Why are you saying $25 million? Why is hallucinating? So we use the word hallucinate to describe this situation when LLM is saying something that just doesn't match reality. And in reality, I'm only making like much less than this. So think about it. You can type in the chat. Why would LLM say, how much does Tom make? Why would it say $25 million? Let me see whether anyone for something reasonable to say. So the hint is that there's someone who's also by the name Tom, who's much famous than myself, who's making a lot more money. Okay, so that is what for you to think about. So without the augmenting your query with a context, it will probably just make the most educated guess. And by searching the internet with Tom, how much Tom make, the most likely you will bring up information about Tom Cruise, who is making $25 million, making Mission Impossible, and they will use this information to provide your answers. So anyway, this is a way that I'm trying to go from RAG and going back to when we didn't have RAG, we only have large language model, how it might hallucinate. And there's another way of saying that one of the original motivation for us to use RAG is to deal with the problems hallucination. The large language model answering questions just based on the training data it has received. And with RAG, we augment with the data we want the large language model to focus on. In this simple case, is that database of our own data. So that's the spirit of RAG. And so in next section, I would like to show you a few more examples of prompting. And the example I just showed you is about question answering. And if we would just add a bit more stuff to the prompt, we can get RAG to serve other applications. So I'm going to go through some simple one. So for instance, we like the RAG to summarize information, and we'll just change the raw prompt very slightly and to achieve the purpose. And this is the actual prompt I got from GitHub from Llama Index. So that's how exactly how you implement RAG. That's to support various application. So for instance, to summarize, in order to summarize, so we'll write something like context information from, instead of just one source, you have multiple sources. So have lots of stuff. So context is could be multiple document. Each document can be really long. So it's a huge text blocks being added here. So multiple sources is below, and given information from multiple sources below and not something. So answer the query. Why would you put it here? So not something we want to prevent the large language model from hallucinating or adding something not relevant is that we won't say, no, not, please don't add any prior knowledge. So we'll ask large language model not to rely on some of the training data set you might have seen. Don't pay attention to how much Tom Cruise made, for instance. So we'll summarize all this text in this context string, and then query string will be coming from the user interface maybe, and come up with the answer. And this thing goes to large language model. Give you an idea. So that is one example. And then another simple example is how about choosing a single choice question? Get large language model using RAG to answer a single choice question. What would the prompt template looks like? So some choices are given below. It is provided in a number list, 1 to a number of chunks. So maybe there could be 100 chunks. We talk about how those chunks are. For each item in the list correspond to a summary. So we'll use database to retrieve a list of context. It'll be 1, blah, 2, blah, 3, blah, and fill up the template over here. And using only the choices above and not prior knowledge, because see this one more time, not prior knowledge. So design this prompt engineering, this seems to be important to prevent LLM, to tell LLM to focus on what I want you to focus on, which is my data, not prior knowledge. So then return the choice that is most relevant to the question above. And then query string comes from our user interface and provide choice in the following format, answer, number, and explain why. That's sometimes for choice. We'd like to then explain why the choice was selected in relation to the question. And there's one kind of technique that when you actually ask large language model explain, that is called, then oftentimes large language model engage in chain of thought, and they will actually do a better job. Knowing that you have to explain this, it will force the language model to actually go through the reasoning to pick the choice. So this turns out to be quite effective to add another explain why this choice was selected at the end of your prompt. So, and then, okay, just one more example, but there's many other examples. They just give you a sense of taking you through how you would, if you ever have to design your RAG, design the prompt. This is the process that you'll go through. Just come up with this prompt, but I just take you slowly here. So refine the original query is as follow query, but we have provided an existing answer. In this case, we're not asking large language model generate a new stuff. We have actually quite an answer maybe from our database. We want large language model to refine it. So we have the opportunity to refine. So tell the large language model to refine the existing answer with some more context below. This comes from the database, and give the new context, refine the original answer to better answer the query. If the context isn't useful, just return the original answer. You don't have to refine. You could just keep the original answer and the refined answer and send all this to large language model to continue to provide the refined answer. So I show you four applications: the QA, summarize, single choice, and refinement. There's a lot of other applications, but finally the similar process. When you design RAG, you would design this kind of prompt. And then you add those prompts to the context you retrieve from the database, and then you add them together to your query and send it to large language model to provide behavior you want. So that is how the prompt part of this RAG equation. All right, hopefully that's helpful. And now we're going to take a deep dive into how the context work. How do we actually get context information? So it comes from database, and before we could even have anything in the database, we have to build an index. And so the index process, I want to go through the index process. They follow a 4 major step, which is to load, split, embed, and store. And then I would like to surprise you with a Chinese lesson. So you have to learn the Chinese character from me. I'm just kidding. No. So the reason why I like to use Chinese because that to convey to you that this process is actually agnostic to languages. It could, if you work for Chinese, it work for other languages, work for English as well. So not just, it's not the English only process. And so first load is that we would like to load a lot of documents into our pipeline. So it comes from your proprietary database or use SQL or somewhere, then you would like to load the store index in a way that you could support your rack. So in this case, those are those 3 documents, and it could be potentially more. And I make a mistake. This should be a unique ID, so maybe ID 3, ID 4. So this is the properties of metadata for document, and these characters are the content of the document. And then split is that we like to break this document into chunks. So for the document 2 and 3 that's already done, you can see that you can kind of tell how many tokens are there in each chunk, right? You don't even have to understand any of the character, but you can just count that three. So chunk size comes to 3. So with chunk size 3, so it's kind of like this 3 and this, another 3, another 3, another 3, and it'll fill this up into the chunk. So actually, I'm gonna so because like this. So first chunk will be the first character, second chunk, and the second chunk, third chunk is this. And the last is this. So you don't really have to understand what these characters mean, but you can see the process, how a paragraph broken into chunk of the same length, 3 in this case, but it could be more. So in Chinese, I can read for you. 大人吃大包子，小孩吃小包子. And then once this is splitting into 4 chunks, in this case, it could be more chunk if we keep going in this document. Now we're gonna take this chunk for this chunk to go to embed, compute embed. So we're gonna use just first 2 chunks as an example. We can do more for all the chunks for other documents as well. So what we're going to do, I'll copy my word down here. This is the first 2 chunk. And by the way, if you're curious, this is character for big, 大. So it means big adult, big people eat big dumplings. So that's what it means. So, and then for this character, we're trying to compute first word embedding. So it's word embedding. So each word will correspond to some vector 1100. So they could be looked up or use some, usually we looked up and from a pre-computed matrix. So in the vector database lecture I did earlier, I went into more detail, but for now, I'm just going to give you the gist that word become a embedding vector. So a single word become 1100, another word become 1001, and so on. And for the next chunk, similar process. So this because it's the same character, you expect that the embedding vector is the same 1100, which is the same as this one. All right. And then for now we have 3 of this, and we would like to merge them into just one. And then this we call sentence embedding. Over here, just one single vector. You go from 3 vectors to one single vector. And there are many operators we can use to combine them. And for the purpose of this illustration, I just use the simplest one, which is just sum them up. So we sum them up. So this will be 2. This is 2. This is 1, 1, 2, 2, 1, 1. Just summing out across the columns. And so this will do the same thing. So get 0, 3 here, 1 here, and 2 here. So this first chunk with this embedding process, the result of embedding is get one single character vector 2, 2, 1, 1. Similarly, for second chunk, another vector. Now we go to the last step to store them. To store them, we have this database is at least 3 columns, but can have potentially more columns, but minimally 3 columns seem to work quite well for a purpose. And for first chunk, we'll store what is in the chunk. So this is actually the first, these 3 characters. We're gonna put it down here. And now we have an embedding vector, which is this one. So 2, 2, 1, 1 for this embed column. And for beta data, we're gonna go back all the way to where the document came from. So go back to the document where the chunks came from. So in this case is this ID and the date. So this ID suppose says this is a blog article. So the ID is 1, date is May 10. And for second chunk, so have store the this three characters from here, and the embedding is 0, 3, 1, 2. And then the metadata actually because they even though they are different chunk, they came from the same document, they will share the same metadata here. Document 1, same date. So you keep you will just keep continue this process to until you put all the chunks. You can just visualize how many chunks they are. 4 chunks document 1, another 4 chunks from the second document, another 4 chunks for the third document. So it is in this example I have on this slide, we can expect to have 4 times 3, 12 chunks over here. Of course, in real life application, you have hundreds of documents, if not over thousands of documents. So it could all the way go to like maybe 10K documents. And each document, instead of just 4 chunks, you could have 10 chunks, 20 chunks, and 30 chunks, depending on the chunk size. And so this says we have 100 chunks per document. So you can see altogether it will be 100, about 10 million. So they will give you 10 million rows in your vector database. Okay. So there's like in the production, you have that many rows to deal with, and you will have to probably use the database solution. Okay. So let's take a bit little talk about loading, split and embed and store about this indexing process, just a bit more. I want to show you some useful tool you can use for this process. And for the unloading part, and there are repositories such as like Llama Hub. They have a bunch of data loaders. You can choose from their own open source. For instance, you want to load data using CSV, you can look it up and say, oh, well, CSV reader, that's what I will use. And which loader to use, you want to read Word document, and there are people have done that for you as well. So there's a docx reader, you might download that along with Llama index. We use other tools, you have something similar. For instance, you use LangChain, there's something similar. You can choose from lots of these read loaders already available you can use. And on the splitting part, and I want to highlight the most important parameters you can control the split process will be the chunk size and also the chunk overlap. So, and token text splitter is just an example of the library you can use to split your data. And I did it earlier just by hand, but this is token text splitter will do exactly what I was doing, but this automatically. And chunk size 4, and illustrate, if you use this chunk size 4, so we're gonna just this one chunk, 1, 2, 3, 4, another forward, another chunk, 1, 2, 3, 4, another chunk, 1, 2, 3, 4, and so on and so forth. So there's token text splitter, each word is the token, and split, then become a chunk, and it will feed to the embedding. And if we have an overlap of 1, what does it mean? Let's use a different color. It means that, well, how are you doing? But for the next chunk, we're gonna repeat the last word, doing today, I hope. And for next chunk, there's overlap 1 more, hope you are doing. And then next chunk, what is the next chunk? Doing well, whether you were. So have overlap, you can deal with this boundary issue, like some sentences cut into half. So you'll never really learn the structure with full sentence. But with some overlap, you could cover this boundary slightly better. And there are some more intelligent method for splitting, but in this case, just want to highlight that what chunk size means, what overlap means. So this is the example. And for embedding part, after you split them, you want to embed them. And the tool is kind of helpful is that usually have a question. There's so many, seems like there are tons of embeddings you can choose from. How do you even begin? So one place you can begin is go to Hugging Face, massive text embedding benchmark. So you get this like massive table with all these embedding models. And so we could get pretty much overwhelmed by this. But then I want to just give you some example, the process of selecting the embedding looks like. So for instance, well, I would like to know maybe 7 billion. I've been hearing people using 7 billion parameter models. And so then you'll go to this column to find, well, this is which model has 7 billion parameters. And so the unit is million. So this is 7B, not 7B. This is 7B, 7B. And then and then another 7B down here. So these are the Meta Llama and 7B models or 7.5. It's close enough. So these are 5 candidates for 7B. And you can see that. And the next one is the memory usage. So memory usage is just proportional to the number of parameters. So this is 1B. This is only 4 gigabytes. 7B has 26 gigabytes. So this how you use this table to help choose. And then, so if I ask you, which model has the most number of parameters? So again, we'll go into this column and find out this is huge, 46 billion parameters. And this is great large language model, 8 times 7B. And you might ask, 8 times 7 is, what is 8 times 7? 56, but it's 46. So this take-home question for you to figure out why is 46 not 56. All right. And which model support the longest context window? Which column we have to look at if we like to know how big the context window we'd like to fit? So they correspond to the chunk size. Earlier we used 3, so the context window just need to be 3. But they now have a longest context window. So it turns out this is the column we want to check. The context window is basically the number of tokens you can feed to the models. So which you go down the list, which one is longer? So you have this 32K, 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 32K. These are simply the longest, but there's a short. Also, there are some shorter ones, 2K, 4K, 8K, and K. So if you really need really long context window, you pick this one, but not the other ones. And some other consideration like the actual downstream task for which model has the best classification performance, you will do that, go to this column. And so, well, the classification average. So this one is highest. Then you use for this voyage instruct model. And if you would like to do the clustering performance, you check out this clustering task, go down. It's kind of close, but there's one, which one is highest? So this is slightly higher than the others. So you use this GTE01, this from, I believe from Alibaba, I think, from the Chinese model. And last, I would like to show you how to interpret this model. Go a bit deeper. You might see this diagram if you've been following my AI by hand series. So this is a transformer AI by hand example I have. So if you don't have, if this is okay, you have not seen it, but you have. So this is the input. So I'd like to see that with the 2 numbers. So this takes embedding 3 largest from OpenAI. So if you pick that one, so you have embedding dimension of this 3000 and max token of this. So where do this number correspond to this metric dimension? So 3000 correspond to this vertical dimension, like the length of how many rows we have down here for each column. So A191 is correspond to here. So go this way horizontally. So in this case, we have 5 in this total example, but you could extend to A191 if you use this text embedding. And this example have 3 rows, but you can extend to 3000 for if you use this embedding. But the transformer architecture is still the same, metric multiplication, down attention, and feed-forward network. Okay, this is probably the most technical slide I have here. And lastly, to store, you could use a resource like from SuperLink. They publish a comparison of all the vector databases and a bunch of columns. So we'll just as a practice, suppose I picked my embedding, which is the embedding I just showed you, the text embedding from the OpenAI. If you remember, the dimension is 3072. So if you look at this, they'll tell you these are unlimited. It's kind of okay. And this is 3000, okay. But this most likely designed for this embedding. So okay. Now okay, it's 2000. Okay. 4000. Okay. Now okay. So you kind of use this as a good resource for you to choose as some other fields, like whether they provide sharding, how scalable they are, and so on. So that's how you choose a vector database. So which database can fit 3072 dimension? I just solved it in the previous slide. I should have do the exercise here. Anyway, and then lastly, we have so we finished the this stack for index. We're going to talk about retrieval. And for retrieval, if you use a database like single store, it provides very reliable storage. It could, if you are technical, you can write SQL statement to retrieve data from the database, you will say something like, what would be this SQL statement, the pop quiz? You'll do like select, and then this is a query that you already embed into assuming we already embed into a vector 0 to 1, 1, the 4th dimension. So this is a special symbol that single source support for you to compute embedding field and dot product with this. And dot product give you similarity. So we've ordered by the similarity score. So high score is good. So we like them to organize a descending order instead of ascending order. So in my vector database lecture last time, I gave a bit more details about this process. And you can also high-level APIs such as superlinked. So they hide a lot of complexity. If you are not comfortable with SQL, you can use a high-level API. You do something like query design a query, give the index, and then you could just out. I want to find the post I want. And then based on similarity matrix, so I want it to be similar to my relevant, according to this particular space, particular parameter, I want to look for my comment field. And then when I actually run this, I just set the comment parameter to be my query string, how are you? And then we'll achieve the similar effect of retrieving something. And once you retrieve, why do we want to retrieve it in the first place? Because we like that to be put into our template for RAG time prompt. Okay. Now I guess I still have time, so I'm going to take you through a few advanced RAG architecture and use this drawing scheme I created, hopefully to help you understand how RAG could evolve and support other advanced application scenarios. So now I'm kind of going back to more like a review for a regular RAG. And so suppose we have a user. When the user issue a query, so we'll go into here. Actually, I want to use a different color. Use a red. The user issue a query, and if without RAG, we just send this query directly to large language model and get our answer. And with RAG, we like to augment this query with context. And the way to do that is we'll send the same query to our database. And the database is going to look up relevant documents. For instance, in this case, maybe document 21, document 43, document 39. These are the 3 relevant documents. And together with this prompt to tell large language model to be respectful, honest, and so on. And then at the end, we send this whole thing to our large language model. And large language model hopefully can produce a much better answer to our user that will minimize the risk of hallucination. So let's review this component, and you can see that. So what is each word R? Where do you see R? Where do you see retrieval? R is here, retrieval. Retrieval. We retrieve from our database. So this thing's retrieval. How about augment? Where do we see augmentation? So augmentation is this box. We augment our query with a bunch of stuff. So prompt plus our context, these 3 documents, and query. So augmented with these 2 things. And then at the end, we use large language model to generation. So this is why we have RAG equals prompt plus context plus query and plus LLM. So that's the equation that help me understand what RAG really is. Okay, so quick review of what RAG is. And the one way we can extend this paradigm is when we send query. So this just a quick review, and then we retrieve down here. So what if we want to retrieve not just by one field, we can retrieve by multiple field, meaning multiple spaces. So we say we have one, we want to restrict by description field, and then we retrieve by headline and so on. 2 instead of just 1. And then we would like it to be something like, well, retrieve based on these 2 spaces that combine somehow, you can retrieve this document like 21, and the rest is still the same. So this is the first extension I'd like to talk about for the multiple embedding spaces. And one way we could do this in a simple way is to use a library like Superlinked, and they provide this library for vector compute. So I can kind of walk you through how it looks like. So still start with the query like who, suppose someone went who won NBA. If you are, I'm actually my hotel is just right next to Lakers Stadium in downtown, so I got to see they already eliminated, so I don't see a lot of actions. But anyway, so I have this question. I can use this API as app.query, and this will be kind of populated this query text field. And a simple query defines how we like to query by different multiple field. And what's important is we have this weight 110. We're gonna talk about what this weight is gonna do. So this table, we have ID, these vector databases that follow a similar process I demonstrate to you, 3 column, but the four, and they're already embedded into this embedding. And with that, so what will happen is that then we'll take this query text, we use the same embedding model, and it will compute an embedding for this. So for instance, for first field will be 1, 2, 3, 4. So we'll just use any arbitrary number to represent, say, suppose this embedding give us 0, 2, 0, 3, say embedding 1. And then we use another embedding. This all kind of happen under the hood. This second embedding will give us another number. This second embedding has different number of dimensions, just so that to show you that it's possible to have different number dimension. So second embedding maybe give us 0, 2, 0. And the third thing is about time. So it's not embedding, but some kind of mathematical equation give us 1, 1. That's, oh, we actually don't quite, I like this to be older or something by time, by recency. Who won NBA? I'm talking about like this year, a season not over yet, but last year. So this is a bit opportunity for to specify that. And if you've been following my AI by hand series, you know that for computing using this input vector to look up vectors from our database, the the mathematical operation is dot product, and to take dot product, we can do something this like this. 0, 1, 2, 0, 2, 0, 3, multiply dot product with 0, 1, 1, 0. And for another one will be this like this. And the third one will be use it like over here, and then we'll compute this number. So this whole row and whole column, we compute the dot product and we get this number. But hold on a minute. I just talked about we have this weight thing. So weight is that we're gonna put weight 1, 1, but 0. So if we put weight 0 here, means that we're gonna ignore this one. We only have to pay attention to blue and yellow here. Anyway, so as a result, when we compute this, we get 5 here, and 3 here, and 6 here. So this is a similarity based on dot product. And the higher the better. So 6, in fact, this is how this number is. So it turns out this row is the most relevant, and it will be shown in the result object, and output will use like 2 pandas to will give you a data frame. Then you can do display the data frame. Then you'll be able to see your notebook. So this is a way you can implement a multi-dimension, multi-embedding in the adding multi-embedding to your rack. And then let's talk about some other architectures I'm going to show you for this rank GPT. The idea is that we'll still similarly we start with a user, and then we'll add user will specify a query, and then you will use this query to go to the database to retrieve a bunch of relevant documents just as before. But we have this extra step before we send this to the LLM. As is, like before, we'll just take the whole thing with query. We're gonna ask LLM, a first question is that, can you re-rank this document in a way that based on their relevance to the query? So ask LLM for this, not previously we'll ask DB for this to retrieve the tree document. We want the LLM to recheck the result in this what it is. And LLM going to say, well, this is our number 1, this is our number 2, this is our number 3. So we rank this. And then it turns out if we do that, then we feed this re-ranked prompt back to the LLM really serve the query, we get much better result, less hallucination and so on. So there's a re-rank GPT, and you can see that the actual prompt underneath you will be saying something like, well, rank the passages about based on their relevance to the query, and then should be listed in descending ascending. Again, so descending order, going from the most similar higher score down, so descending, not ascending, and do not something. Also, do not explain, because we only ask them to re-rank. If we add this, they're just going to say a whole bunch of explanation sometimes, but in this case, we can only care about re-ranking. We're not asking it to make a single choice to justify. We just ask it re-rank. So do not explain, because we're gonna use this result to feed back to the LLM and to get final answer. Then in that case, it can explain more. Okay, so this rank GPT. You might have heard of multi-query retrieval. What does it even mean? Let's start again. We start with the user, and then we send query to this, and then normally in the rack, we'll just send this query to the DB to get these three things. But instead of doing that, we're going to send this query now to the large language model, but not asking large language model to answer, but ask large language model, say, hey, can you come up with some other query that kind of similar to this query and diversify the perspective? So large language model give another query question, similar question, a derivative of this question, another question. And with this question, and it's going to, then we send this, they send this question query to the database to get a bunch of documents, send this query to the database, get a bunch of documents, and send this query to the database and get a bunch of documents. So you can expand the context from 3 documents to 9 documents. Do you see that? And then with that, and we send the whole thing, I want that purple, to the large language model and to get much better answer to this. So just multi-query retrieval. Hopefully that makes sense. And to implement multi-query retrieval is not super magical. It's just basically saying that you are the AI language model system. Your task is to generate in my previous case, 2 different versions of the given user question to retrieve relevant document from a vector database. And by generating multiple, and it tells you the purpose. Why do you want to generate 2 different versions? Because we want you to generate multiple perspective. So have a more diversity in our answer on the user question. Your goal is to help the user overcome some of the limitation of the similarity-based search. So we use only similarity-based search, referring to the database part of it. It only uses similarity. It doesn't provide a lot of perspective at a high level. And with this case, it's multi-query retrieval to provide more diverse answers. And lastly, the last, actually not lastly, a contextual compression is another way to improve RAG. So start with the user again, but then we'll send the query, and then we'll generate. Normally we'll generate send query to database to get documents, and the query tend to be pretty short sentences. And then we have some keyword matching or vector matching for database. And then the contextual information compression is actually still send this to the database, get a whole bunch of query. And normally you send the whole thing to large language model and send this document in context as is. But for the contextual compression, idea is that what if we, instead of sending the whole thing to large language model, because this document can be really long, the part that's really relevant to a query could be just a part of it. So the idea is, what if we send the large language model this to check this document and query, and ask language model, hey, can we just find the relevant part for each document, relevant part to query? So large language model will say, hey, for this document, this part is relevant. For this document, maybe this part is relevant. For this document, maybe this part is relevant. And then afterward, we just delete the rest of it that's not relevant. And then we use this compressed version of context and send this to large language model. And that it turns out to improve the preciseness of lots of answer to make language model more focused. And last is the hypothetical document embedding. The idea is that we still start with the user as usual, and we send the query to here. And normally we'll send query to the database, but instead of doing that, we would like to say, hey, can I get a more extended form of the representational query? And the form is we ask the query large language model to look at the query to just, oh, how about you just guess what the answer would be? What the hypothetical answer? What would be the relevant document look like? Ask large language model to guess. So we call this thing a hypothetical document. And then we use this hypothetical document to query our database instead of the original query. We get the relevant document. And the advantage of this is that the database has a lot more. So for instance, get 17, 23, 12. Database has a lot more keywords in your hypothetical document for you to look up relevant document. And with that, then we take the whole thing, augmented query again to large language model and get user. Okay. All right. So I did succeed to cover everything I'd like to discuss today. I even went through a few advanced techniques for you to get a taste of how you, as you innovate, use more advanced techniques. Really about just adding some change this path of this a little bit, add something to it and reorder something. But then at the end of the day, a lot of times has to do with just modifying underlying prompt for you to do what you want. It's not super magical. Hopefully you give a bit more idea what it is.